Hi, hello. Today we are going to talk about another coding pattern, backtracking. So our flow discussion will be as before. First we will talk about what is backtracking, then we will talk about how we will identify the problem, then we will look for the coding template, and finally we are going to explain in more detail. And on the right hand side I have mentioned few questions which are related with Leetcode problems, so you can solve them by yourself. So if you have heard any questions, like they are saying there is a grade, let's suppose you have 4 queens and there is a grade of size 4 by 4 is grade, and you have to place all queens in such a way, like you put them in such a way that they are not a threat for anyone. So in that case you have to return the answer. Or if there is some question which is being asked, let's suppose you have a grade and there are a number of characters here, let's suppose A, C, D, X, Y, and they have given you some string and they are asking you how to find that if you could make this word from this matrix. Or you come across some questions like permutation or with combination, or any question which is belonging to combinatorics. So all such questions is going to be solved using backtracking. Even your Sudoku problem is going to be solved by backtracking, like generating parentheses or palindrome partitioning. So any questions where it sounds like you have to incrementally make some answer, and due to some particular condition you have to move back, so you have to incrementally have to make some solutions, and due to any condition you have to backtrack. So for such questions mostly you are looking for backtracking. So after this video you will be quite proficient to solve any such questions which is related with backtracking. I'm very honest with you, there are a lot of questions which you can use backtracking and solve them easily. Let's go without wasting time and we will see what is backtracking. Alright, now let's see what is backtracking. I have mentioned a little bit details here. You can read out like these 2 points which were explaining what is backtracking. I can explain myself. So from backtracking you can consider it's like a brute force. So you already know that this is going for each solution, every solution, without considering any constraint that is it satisfying or not. Backtracking is like a refined brute force. So it takes a decision on each node that he has to move forward or he has to backtrack, considering on some constraint. So he take care of the constraint that if he has to backtrack or on the satisfying condition. So if he found some possible candidate, so in that case, let you find some candidate, in that case he is going to undo one by one to find other possible solutions. I can explain in a very simple example. Let's suppose if there are 3 persons, father, daughter, and mother, and daughter has a wish that she wants to take her picture and she must be in the center of that picture. In that case, this is a condition which we can call it's a wish of daughter. So in that case, it must have to be satisfied. So we should not consider other arrangement. So let's see here, we are going to draw some state space tree, and here we go. So in this state space tree, you can see that these are number of possible arrangement that father, daughter, and mother can take place. Like here you can see this is the first chair, second and third chair. So in the first chair, father can sit, then mother, and then daughter. And the second arrangement is father sit on the first chair, then daughter and mother. It is very clear that from this picture you can see that if mother is sitting in this first flow, if mother is sitting in the center of the picture, we should not move forward. We should not consider that we are going to find some possible candidate from here. In that case, there is no need to traverse this subtree further. We should just backtrack from there. So that's how backtracking is taking decision at this point, and it is going to backtrack. And here you can see if daughter is sitting in the first chair, there is no need to traverse further. So we can skip all traversal of that subtree. And in this place you can see mother is sitting on the first chair and father is in the middle. So no need to go further to find any solution. So So we should skip this subtree, and from here we have to backtrack and move for other solution. And you can see from this picture there are two possible solutions. This is the first one, father, daughter, and mother. They're sitting in this arrangement, and the other one is mother, daughter, and father. That's a second arrangement. So these are the two possible arrangements that we can achieve from, and backtracking is giving help by not traversing and taking decision on these nodes at this place, at this place, and they're backtracking. Another thing you can see, traversing is coming to this point at this leaf node. At this point, it has already found its solution, which is father, daughter, and mother, but it never stopped here because it's a brute force. He has to look for all possible, all feasible solution. So he will backtrack and start undoing. Undoing means that undoing operation is being taken at two places when your condition is compromised. Like you can say on the center chair, father or mother are sitting. That condition is being compromised. In that case, we have to take the decision at that particle node and we have to backtrack. The second condition is when you found some solution and now you have to look back to find other possible solution. So you found a solution, you save it, and then you're going to undo one by one each element. Remember, this is one by one. It is going to remove each element to find other possible solutions. So we found the solution by adding one by one. So note that to find the solution, how we are traversing, we pick our one element. We ask one question: have we compromised the condition, or we have found the solution? If we have found the solution, in that case we start undoing. If we never found the solution, we never compromise the condition, we keep on adding our new element. And we again ask these two questions and we keep on adding new element. So in this case, incrementally, we are adding new element to find our solution. And on compromising condition or finding solution, we undo one by one each part and we try to find other possible solution. So this is how backtracking is working. Remember, don't get confused with recursion or with DFS. So recursion means that you keep on going forward until you find your base condition. So once you find the base condition, you just move back. And in DFS, this is the way of graph traversal. We are going in depth and until you go to the leaf node. This is the way this graph traversal is going on, and then it goes back to go to other path. But it goes deep down. For sure, backtracking is taking the benefit, like it is only going with the DFS the way it is going to traverse. But this is the way of graph traversal. But backtracking is a technique. Backtracking is a technique which is taking a help of DFS and going to find all possible solutions. So this is backtracking and recursion, the difference. I will go further and I will explain further in detail that what are the difference. Now let's go and we go how we will identify any problem. We have to use backtracking or we have to go for using some other coding pattern. Let's see what are the possible points how we can identify the problem. Alright, so in this part we are going to talk about it, how we will identify the problem. That do we apply backtracking or we should move for some other thing. So these are the points which says yes, you have to use backtracking. And these are the points when you are saying it looks like we can apply backtracking, but we should not. So let's see one by one each point. So when we are saying the first point, when we are talking about like to decide for the best solution, we need to have all feasible solution in hand. You can see traveling salesperson problem. So if you are looking for the best solution, you need to have all possible feasible solution in hand, and then you can decide that which one is the best solution. For such problem you can use backtracking. Second point says when they're looking for all feasible solutions. So in your question, so that was the point one. Second, in your question when they're asking for all feasible solution, like when they're saying provide us all feasible solution when the daughter is sitting in the center of chair And so you can say father, daughter, mother, or you can provide another combination, mother, daughter, and father, where daughter is always in the middle. So such problem where all feasible solution is required, you have to try backtracking. Third point, when we are saying like for finding any candidate solution, explore all paths. So you have to go with a DFS, and then you are looking all across path, like you try this path, like if I will say you try this path one by one, picking some element. If you never found, you go back, you try other path, you never found, you go back, and then you keep on trying different path. If you find some possible candidate solution, you save it, and then you try other path for this. So for all those questions, you can for sure try backtracking. And when we should not use backtracking, even it looks like you can use them. So first, I'm talking about this point. So just one feasible solution is needed. The same problem when they're asking if the daughter has to sit in the center chair. So you can, and they just need one solution. So you can provide father, daughter, and mother. That's the one. So once you find this solution, like you keep on moving, you find father, then mother, and then you try for, let's suppose, daughter. You never found because you are on the leaf node. You go back, and then you keep on moving forward because this is like a tree traversal. So you come here, and at this point when you find daughter, and then your mother is at the end, so you found this one solution, father, daughter, mother, and after that you just have to go back to the root node and you say yes, we have found the solution. So when only one feasible solution is needed, in that case you are going to just use like DFS. It's not good to use backtracking because backtracking has to look all feasible solution. Now the second point, when we are saying constructing a candidate solution, if including an element compromise the constraint, and that applies to all of the remaining elements too, means there is no reason to try other elements by backtracking because they will also violate the constraint. It means that I'm saying, let's suppose if they in the graph they're saying this is node A and we have to go to node S. So they are asking find the minimum path to reach to node S. In that case, instead of using backtracking, the best possible solution, because if you go with the BFS approach, or you go with the approach like branch and bound, so you can get the solution in better way, or in such cases you can use digestrua to solve the question. So instead of going with the BT like the backtracking where you have to traverse all the path, so instead of going with this approach, I will better say that you should better go with digestrua, or you can pick BFS approach, because on level wise you know that what is the cost once you're on the top of the level. So you already decide that, let's suppose at this level you know what is the cost of this and that, and on the next level you know what will be the cost of this node and this and that, because you are going level by level. So once you compromise this situation, you don't need to try other path to backtrack. So branch and bound is like, it is following BFS approach and it is branching, like it is going to each branch, and if it found some bounding function is just like which we are talking about like a constraint in our function. So branch and bound says that you go to the branch, you find a bounding function, and then you have to go back. But it is more intelligent, it is going for optimal solution, and it is approaching BFS approach. So we are not talking about that, but let's talk about this backtracking coding pattern. So yes, that's the second condition when you should not go for backtracking. So these are the point where you can identify any problem. And for sure there's one more point that you can consider. Like any solution which you're going to create, you pick again, you incrementally create your answer. Like you pick the first element, then as I had told before, you pick the second, then you pick the third, and if you found your solution, you undo them one by one and you go look for other. So you incrementally create your answer and you decrementally go for finding other solution. Now let's go and find what will be the coding template for backtracking. Finally, so we are going to talk about coding template. It is very simple. Here I have mentioned a very simple example, which is talking about that we are going to give you n number of elements or n numbers, and you have to provide all possible combination of size k. So such problem you can use using backtracking, because you can see that number of combination will be 1, 2, 3, 4, or 1, 2, 3, 5, and so like that. And what will be the coding template? So you are going first, you say this is my backtracking function. You provide all the possible number of parameters that you're expecting. Second, here when you move forward, that's the first if condition, which is normally saying what is when you find the solution. So this condition is looking for when you have possible solution. In that case, you can save that solution in all, like these are the possible candidate solution. So these are the possible candidate solution you will keep on adding once you find that. Next, you move forward in the else part. Forget about that. There's a for loop which is going from start to n. So this for loop is going to change with each iteration, like it is squeezing from start to n. Then it is going to change from 2 to n. So initially it is 1 to n, and then it is going in the next iteration like 2 to n. Then in the next iteration it is going for 3 to n. Not iteration, sorry, it is like a backtracking call. So with each I will explain further. So here in this coding template, you can see there's a for loop, and then here is this part where we are adding the first element. We are saying, okay, pick this element and see if you could use this element and you could possibly find some possible solution. There is a candidate solution if you find that. If not, in the next line we add, and then next line we are going to call the backtrack function, and we are saying go and find if you could possibly get your candidate solution. If not, you get back at the end, and finally we are going to remove here in this loop. So the flow is pretty simple. You have your condition which says you found a solution. If yes, save it. And in the for loop, what you're doing, you're picking one first element and you're saying call the backtrack function again recursively, and there you're saying we have updated our combination and see if you could find the solution. No. Once you get back from this backtracking call, we will remove that last element and we will keep on doing this again and again. So the flow will look like something like this. So here, this is the if condition. If the condition is satisfied, you are going to save your solution. Else, what you're going to do, you are mostly making a for loop, which is with each iteration, with each backtracking call is squeezing. So you have the for loop call, you add your element, then you make a backtracking call recursively by changing some parameter, and then finally you remove that element. So this is how you're making the for loop, which next iteration what's going on, it is going again with this if satisfaction call, this whole condition. If it found the solution, it will save. In the else part, this for loop is going to be squeezed, like this is n time and that is going to be n minus 1 time. And again you are going to add, here you are going to call the backtracking call, here you are going to remove that, and that goes keep on going with and so and so and so. So this for loop is actually squeezing n minus 2 and so on, like this. So this is very simple coding template. Here in this part I have explained the same example what I was talking about, like there is a father and there is daughter and mother. So if we found that daughter is in the middle, we are going to save that solution and we are like moving forward. So I'm not going to talk about this solution, but pretty simple that you can, as a structure, you can see, because here I have used for left, which is scala related. This is accumulator, and I'm just going to add this element, and I'm removing that with each iteration. So this is again the same structure. You will find that you have this backtracking function, and you're going to, if you get your satisfying condition here and here, for sure it can be a combination of multiple. If you found that, you have your solution, you can save that. Otherwise, what you're going to do, you add your element and you are going to call your backtrack. As a whole, the structure is exactly the same when you're going to add and remove with each iteration. Now I'm going to explain further that there could be some confusion, that some people say that recursion or DFS, they're exactly the same like backtracking. They're not. Let me explain a little bit more, and that will be the end after that. Okay, for the quick explanation, I have written here, this is recursive call, and this is, I was thinking, some backtracking function. So for the recursion, I'm taking very simple example like def, which is a factorial. So I'm expecting that we are going to give him some number int, and it is returning int at the end. Simple implementation, base case, if n is less than equal to 0, we are going to return 1. Else, we will multiply n by making a recursive call to the factorial of n minus 1. So in that case, when we are saying factorial of 3, so we are expecting 6. How it is being implemented, like how it works. So here you can see we're going to make a call factorial of 3. So this box, what you are looking at, is like actually the function. When we're making a recursive call of this function, so exactly that function is being placed like of the same size. A whole new memory is being allocated to another function. So it is put on top of this stack. So you already know that we have a function stack. So here we have function 1, which is making a call to function 2. So they keep on adding on top of this stack. So that's why sometimes you see stack overflow exception. So this is because that we make a lot of call and then it goes stack overflow exception. So how it will work, so factorial of 3 is making a call 3 multiplied by factorial of 2. So on top of that, you will get factorial of 2. It is making a call to factorial of 1. It goes up, and factorial of 0. At this point, when we are on the top, this condition, n is less than equal to 0, is satisfied. And now we know that this factorial of 0 is equal to 1. So now he is going to substitute the value. So instead of using factorial 0, he is going to pop this function from the stack and he's going to substitute the value. So this is gone. So it will substitute value 1 here, and it will evaluate that this factorial of 1 is equal to 1. And now that will be gone. So now it knows that factorial of 1 is equal to 1, and that is being substituted here. And now we will calculate after 2 multiplied by 1 is equal to 2. Now after that, it knows that factorial of 2 is equal to 2, and it is going to substitute that value at the bottom of this function. So once it will substitute that value, that factorial of 2 is equal to 2. In that case, we will get the answer 3 multiplied by 2 is equal to 6. So this is how it works. So it goes till it will find the base condition, and once base condition is satisfied, it just goes back to the root node. Now here, if we talk about in backtracking how it works, let's suppose it is some sort of combination call. So it is making a backtracking call that it's saying 3, then 2, and then it's making a call 1, and then 0. Let's suppose it reached to some solution. So at this point, we are going to save some solution, or might be it came back because of the condition is being compromised. So either of these reasons, we remove this from the stack, and we will get back to our next function, and let's suppose it is also being backtracked, it just removed. Now at this point where we were using backtracking 2, because he has already made a call to, let's suppose, backtrack 1, and here it just came back because of any constraint or condition, or he already found a solution. Now he's not going back like recursion is going back. Rather, he's making a call to rest of the remaining elements. So he's making a call to this one, like he's saying go with the backtrack 0. So this will come next. So in this way, if I will show you, this is from actually bottom to top. I was showing how actually it is happening in the stack, but actually if you look for recursive call, it is keep on going down and further down, and once it finds the base condition, after that it is being returned back by popping each element and substituting the values. But in case of when we were talking about backtracking, so it is coming down, it is actually going exactly like a DFS. So he's going down and down. Let's say at this point he found its solution or condition compromise, it will go back, and then he's making call another function. It's going for finding other solution for the rest of the element. So this is the difference actually between a recursion and backtracking. Hopefully this makes the picture more clear, and we will see that how you can approach and solve and identify these questions and apply backtracking with the same coding template. See you soon. Bye.